Hello and welcome to this video version of my FEC 2020 poster. Let me share the screen. There you go, share. I hope this is visible now. It's about the analysis of the interspecies power balance in jet plasmas. And that's poster material which has been adapted to circumstances, which makes it a slideshow. The motivation for the study is that the ion temperature from charge exchange recombination spectroscopy in jet IOW is most often difficult to analyze. There are long delays. Often they remain unavailable, and there can also be inconsistencies. And all this is due to tungsten nuisance lines. Therefore, we need consistency checks. TI can be lower or higher than TE. It's especially higher than TE and in high power DT scenarios. Neutron rates, which are of course important to us, depend strongly on TI, and so we need better surrogates than simply assuming that TI equals TE. Power balance is also an essential part of any transport study, namely for the comparison with gyrokinetic modeling. I'll talk about ion-election power balance in jet, equipartition temperatures. I'll tell you the fraction of ion heating source that goes into the electrons by equipartition. Then I'll talk about the main ion and the impurity power balance, comparisons with trans, and finally the application of all this to TI profile reconstruction. The electron ion, or rather ion-election power balance is given here. The balance equation for the main ions here is given as the net ion power is the source power minus equipartition with electrons and the impurities, and got a similar one for the impurities themselves. All of these powers are understood as being volume integrals from the axis to any point you want along the radius. This is a general formula for equipartition between two species. The A's are atomic numbers, atomic masses, and the Z's are the charges. The example on the right shows a power balance for the ion with QIS here, the source power for the ions, QIE, the exchange with electrons, and QI, the net ion power. The delta QI over QI here has been evaluated assuming that delta TI over TI is 15%. Another way of looking at this power balance is to ask yourself, since I know TE rather well, what would TI be as a profile if a given fraction of the ion electron deposited or electron deposited power was transferred to or from the electrons by thermal equipartition? The curves above the electron temperature, which is here in blue, give this answer for 20, 50, and 100% of transfer. Of course, 100% of transfer is beginning to be impossible because there would be no net ion heat flux left. As we can see here, the measured points, that's those bars, are quite close to the 20% line, and actually the 20% line would provide a good fit for it. So what we have is that these equipartition temperatures are actually families of kind of virtual temperatures defined by this parameter, which is the ratio of the equipartition to the source power. Now, we have in a database called JetPeak a very wide range of conditions. And in this, we have selected cases where the error on the ion-electron exchange term is less than 1%, or less than 10%, or less than 30%. The better ones are the one here shown in magenta and red. As you can see that for these ones, the ratio of QIE, QIS is typically less than 0.25. Now we'll look at the ratio of the net ion power divided by the sum of the ion and electron power, the total power, neglecting radiation. And we see that this is typically in the range 5 0.5 to 0.7 when Ti is larger than Te, and in the range 0.5 to maybe 0.8-ish, mostly for Te larger than Ti. So this situation is typical for ITGs, and it doesn't really matter which of Ti or Te is the larger. The usual assumption that the main ion temperature is equal to the impurity temperature is not warranted at high power and low density. The energy exchange by collisional heating from NBI, ICRH, and even ECH scales as Z squared over A and is hence 10 times larger for neon ions than for deuterium ions. Neon ions are used for charge exchange recombination spectroscopy in jet ether-like wall. The stronger heating for higher Z is strongly counteracted by thermal exchange between impurities and main ions. Additionally, the main ions and impurities undergo transport. A solution can be found for the ratio of the impurity to the main ion temperature with explicit species dependencies, and you can look at it in this nuclear fusion paper. What we see here is the expression I derived for this ratio. Don't look too much at the details. There are two parameters which are important. One is Qi over Q110. Q110 is a reference power, explained here. And the other is alpha, which is the ratio of the heat divisivities for impurities and main ions. This Tz over Ti scales almost linearly with Qi over Q110. We see that there are large differences between the light elements, hydrogen, deuterium, tritium, and helium-3. But the rest of the impurities are fairly closely clustered together, especially for impurities heavier than lithium. We typically have Qi over Q110 less than 1 for most cases in jet, less than 0.1. Here are some histograms that show this. This is in the core, and this is closer to the edge. Here is 0.1. There are only a few that go a bit above. These high values correspond typically to high power and low density, like AT plasmas and hybrids. Here you can see for a fixed value of Qi over Q110 of 0.1, how these Tz over Ti depends on the mass. And this for hydrogen, deuterium, tritium, and helium as background main species. For deuterium, you can see we are near 5%. For hydrogen, the difference is smaller. It's around 1 to maybe 3%. For tritium, we are higher, 7 to 8% maybe. And for helium, there's virtually no difference. Large differences always occur between the light species. The fact that these impurities here have virtually the same Tz over Ti is, of course, very convenient because we can just combine measurements from different medium to heavy impurities. The calculations for mixed main species like D and T is technically similar to single main species. And unsurprisingly, the impurity to main temperature ratio in mixed isotope plasma simply assume values intermediate between those of single isotope plasmas. In particular, in a DT mix at 50-50, we expect the tritium temperature to be a few % lower than the deuterium temperature. This is, of course, not of any consequence for the DT operation itself. There is a similar approach in TRANSP that is incorporated in a routine called SLVTX. We have a data set of over 300 transjet carbon runs that was done for a so-called neutron deficit study, which is published in the nuclear fusion paper in 2018. Stationary state MATLAB version of SLVTX, that means one with time derivative set to 0, was created and compared to our analytical and our iterative solutions. SLVTX is based on the idea of a local confinement time, and it is applied to the same input data as our own calculations here and the INDEES 300 runs. Now what we find is that the analytical method and the SLVTX MATLAB method are virtually indistinguishable. Both of these have a slightly larger ratio of impurity to main temperatures than the iterative, which is the most accurate method. But the difference is so small that it's almost not worth bothering with the iterative method. The difference is, these corrections are still generally only in the percent range. So the intended algorithm behind SLVTX is correct, but the code implementation in TRANSP is not. This can be seen in the graph on the right, which is taken near the core, 0.2 of the minor radius, with the TRANSP ratio here and the analytical version here. We get at the highest values of TZ over TI, which is also the highest values of QI over Q110. Here we got to some 14%, but here only to 7%. At the lower values, there's little difference. Now, if we set alpha to 0 instead of 1, the difference is reduced. And if you set it to -1, well, they almost agree. It's quite a fair agreement, I would say. And this suggests that in TRANSP there is an error, which could be in the sign associated with the ratio of the diffusivities or with the QZ. Another test is to see whether the results of the code, when they reconstruct the profiles, if the ratio of the diffusivities is really 1 as intended. And you can see that with the iterative solution, it is quite close to 1, despite a simplification, which was to assume that the ratio of the temperatures is equal to the ratio of the gradients. In the analytical solution, we deviate from this, so we are typically below 1. And TRANSP does the worst. It's all over the place. And another problem with the TRANSP implementation is that the heat loss from the impurities to the background species is often more than 100% of the available. So that power balance is crassly unphysical. In the iterative method, that ratio is close to 0.77. Now let's be creative. Suppose you're desperate for deuterium temperature profiles like colleague Paula Siren at the IAEA FEC 2020, but you got no impurity temperatures from charge exchange. Well, there's a way out, is to use the nickel 26 plus temperature from X-ray crystal spectroscopy, which is almost always available. Unfortunately, it is line integrated and it is rotationally shear smeared, and as a result, systematically above those charge exchange temperatures which are available and believable. Now, what's the answer? Well, the answer is to regress the charge exchange temperature when available, still available quite a few times, with the nickel temperature and the nickel rotation. You can see that you get a very good fit with a standard deviation of 250 eV, when the highest temperature here go to 9 kV. Then, in the second step, for any measured nickel temperature, you can make this correction based on the fit coefficients and find a corrected one, which is shown here with the open star. And this point then defines you the ratio of QIE over QIS, which I have to assume constant here, and therefore it defines a whole equipartition temperature, which is shown here in black. In this case, you see it matches quite well with the available Neon 10 data, but remember, they are most of the time not available. Then, if you want to push it a bit further, you can make a correction for the main ion temperature based on the on what we've just seen before. In this case, the difference is so small that you could neglect it. One thing is I have to be careful about is that when you have an ion ITB, then all of a sudden you get a huge change in the ion temperature gradient, and this method doesn't work. Okay, let's summarize all this. Equipartition limits how far the temperatures of the plasma species can go apart. In most chiefly ion-heated plasmas in jet, the ions lose up to 30% of their input power to the electrons by thermal transfer. The fraction of power lost to electrons is found to be close to constant for most of the plasma cross-section. In a wide range of jet plasmas, whether Ti is larger or smaller than Te, we find that the ion heat power, the net power, is more than 50% of the total power. And that's a hallmark of ITG-dominated microturbulent transport. The main hydrogenic ion temperatures near the magnetic axis are typically a few percent lower than impurities, exceptionally up to about 10% at high power and low density. The tritium temperature is predicted to be a few percent below the deuterium temperature. For Z larger than 3, the impurity temperatures are virtually species independent, which is convenient. The analytical method and the MATLAB implementation of SLVTX produce virtually indistinguishable results. Both predict slightly larger impurity to main ion temperatures than the iterative method. Someone should actually have a look at the SLVTX routine, which is used in TRANSP, and correct it. The power balance calculation that we've shown here is made good use for at JET by allowing to infer an entire ion temperature profile from a single local or line integrated measurement, such as nickel-26 emission, when charge exchange profile measurements are not available. And that was it. I thank you very much for your attention, and bye-bye.